Okay, in this fifth part, we're going to focus on a particular sequential circuit. That's an example from the textbook, and we're going to go through the process of analyzing this circuit in order to get the logic diagrams, equations, state tables, and finally a state diagram. So this picture on the side is basically the same as what we showed in the very first part of this lecture, apart from the addition of this clock, which we've analyzed during this lecture, the idea of including a clock input to our storage elements in order to solve some of the timing issues and some of the undefined state issues. This is the most general sequential logic model that we'll look at, where the current state at time t is stored in an array of flip-flops. The next state, which is at time t plus 1, is a Boolean function determined in the combinational logic part of this circuit using both the inputs and also the current state at time t. And then the outputs at time t are a Boolean function of the state at time t and sometimes the inputs at time t. Note though that although the outputs may not depend upon the inputs in certain cases, the next state at time t plus 1 does depend on both the previous state and the inputs. So here's the example we're going to look at, and it's from figure 5.15 in the textbook. So the input function is x at time t here, the output is y at time t down here, and the state is a at time t and also b at time t. And really these are the states of these D flip-flops. And the question is, what is the output function and what is the next state function? So we can see we have some combinational logic here. We have an AND gate, another AND gate, another AND gate. We have a couple of OR gates. We have a NOT gate down here. And then we have some inputs to those gates, whether they're inputs from outside or whether they're inputs from inside the circuit itself, such as this A here, or this b here. Then we have to follow that through and then see if we can work out what is the output function, y at t, obviously a function of both b, a, and x. And then the next state functions a at t, which is obviously a function of a, x, and b at time t. And b is a function of x and a, and remembering that a is also a function of b and x. Now we've drawn squares around the combinational logic that gives us the functions for a at time t plus 1, at b at time t plus 1, and y at t. So for a at time t plus 1, we have a at t and x at t, or b at t and x at t. That's this block here. This block down here, we have the output not a coming in here and x at t. So you can see this one's not a. So that's b at time t plus 1. And then the output function y at t is a function of not x at time t and b at time t or a at time t. In terms of the combinational logic, that's quite straightforward. And if you've got your head around the idea of having the next state being at time t plus 1 and the previous state being at time t, then you should have your head around this idea of the next state functions and the output functions. So let's think about the state table for this. If we had a and b being 0, 0, 0, 1, 1, 0, 1, 1, given x equaling 0, x equaling 1, what's the values of a t plus 1 and b t plus 1? 0 and 0 or 0 and 0 gives 0. If we have 0 and 1 or 0 and 1 gives 0. For b, if it's not a, not 0 and 0 gives 0, not 0 and 1 gives 1. So if we were in 0, 0 and we got a 1, then we'd move to state 0, 1. In state 0, 1, if we get a 0, we have xt being common. So if x is 0, then basically a is always going to be 0 no matter what. So we can fill that in. And then we have, if x is 0, the bt plus 1 state will also be 0, no matter what the value of not a is. So we can say that given x equaling 0, then we will always transition back to the 0, 0 state. For x equaling 1, if we have a being 0 and x equaling 1, b at t being 1 and x being 1, that will give a equaling 1. A at time t is 0 and x is 1, then we get 1 for b as well. So that would mean if we were at state 0, 1 and we got a 1 in, then we've moved to state 1, 1. If we're in state 1, 0 and we get a 1, then since a is 1 and x is 1, then we get a 1 for a. t plus 1. Since a is 1, then bt plus 1 will be 0. And for current state being 1, 1, then since a is 1 and x is 1, and b is 1 and x is 1, then a will stay at 1. Since a is 1, then bt plus 1 is 0. For the output, we have yt plus 1 depending upon both the input and also the output. In the case where x is equal to 1, then not x is equal to 0, so the output is always 0. In the case where x is equal to 0, not x is equal to 1, therefore if either bt or at is 1, then we will get a 1. If they're both 0, we get a 0. So we get a 1 here, and 1 here. So if we draw up that state diagram, we've got 0, 0, another state 0, 1, another state 1, 0, and another state 1, 1. We transition from 0, 0 to 0, 1 if we get x equaling to 1, and we output 0. From 0, 1, we transition to 1, 1 if we get x equaling to 1, and we output 0. From 1, 0, we transition to 1, 0 if x is equal to 1, and we get an output of 0. And from 1, 1, we transition to 1, 0 if we get an input of 1, and we also get an output of 0. From 0, 0, we transition to 0, 0 if we get an input of 0, and in this case we output 0. From 0, 1, we transition to 0, 0 if we get an input of 0, and we get an output of 1 in that case. From 1, 0, we transition to 0, 0 when we get an input of 0, and we get an output of 1. From 1, 1, we transition to 0, 0 if we get an input of 0 and we get an output of 1. So notice that we go between 0, 0 and any other state. When we come back to 0, 0, we get an output of 1, and we transition back to 0, 0 when we get an input of 0. Otherwise, we go from 0, 0 to 0, 1 to 1, 1 and then to 1, 0, and then we would stay at 1, 0 if we keep on getting 1s. So it's basically counting up in grey code. Okay, for this example, let's have a look at this signal simulation, starting with an input that we haven't actually shown before, and that's the reset. So we reset the entire circuit back so that it's at a known state where we have A, B, and Y all being 0. And then notice that these clock pulses here, so here's our first clock pulse at time equals t, and this is a rising edge. We have x equaling 1 whilst the clock pulse is rising there. And so when the state is 0, 0 from our previous diagram, which I've just put up in this top right hand corner here, when we get an input of 1, then we have an output of 0, but we move on to state 0, 1. So does this happen here? We are at 0, 0 with an output of 0, and we have x equaling 1 and a clock pulse. Then we move on to state 0, 1 with an output of 0. So that's right. And then at this point here, we have x going from 0 to 1. And when we're in state 0, 1 and we get x equaling to 0, then the output now equals to 1. So this is the output y equaling to 1. At time t plus 1, we have another rising edge here. We have x equaling to 0. Therefore, the state of A stays at 0, but B is now changing from 1 to 0. So we're back to 0, 0, and we also have the output going back to 0. And here we have x going from 0 to 1. However, since we don't have this rising edge clock pulse, there's no change in A or B until this clock pulse has the rising edge, and then we go once again from 0, 0 to 0, 1. We move to there, output still being 0. X continues to stay at 1, and when x is 1 at the next clock pulse, then we have the states going from 0, 1 through to 1, 1. It's this state here. Some more clock pulses here. We're in 1, 1. That means we're at state here, and we get another 1. Therefore, we move to state 1, 0, and the next one we stay at 1, 0, and then all of a sudden the input goes from 1 to 0, and when we're in state 1, 0 and we get an input of 0, then we have an output of 1. So at this point when the input goes from 1 down to 0, then we get this output of 1, and then at the rising edge on the clock, then we have x equaling to 0. Therefore, the states of A and B change from 1, 0, which they were at, to 0, 0. We have another change on the input from 0 to 1. Therefore, at the rising edge, we have the state which was at 0, 0 back here going to 0, 1. And then that's basically the end of the simulation. So you can see that the next state functions and also the output functions that we got to create this state diagram can be simulated in this way to show, given a clock and some inputs that are changing all over the place, not necessarily with the clock, then we can simulate the next states which change on certain places of the clock, in this case the rising edge, and the outputs y, which depend upon the input x at that particular time and the flip-flops a and b at that particular time. All right, let's do another example. Here we have example 2 of sequential circuit analysis. We have a logic diagram, somewhat similar to before. Once again, D flip-flops. In this case, we have 3 D flip-flops. There's a clock connected to each of those D flip-flops and also a reset shown here. We can see again that we have some combinational logic. We can also see that we don't have any external inputs. There are no XTs coming in here. This doesn't exist. So the next state is only going to depend upon the current state and not upon the inputs, which gives us the idea that we might have some sort of counter. So let's once again analyze these blocks as we did before. We can trace this through to say this top line here is B and this next line down is C. A is equal to B and C. Here we also have the analysis, the variables. There's no inputs, there's an output of Z, the state variables of A, B and C. Now the equations for A at time t+1, we've got that as B and C. For B, we have it as not B and C, or B and not C. Not B and C, or B and not C. And for C, I have not C and what's this? This is the output of A. This is not A. So therefore, C is equal to not A and not C. And the output Z here is just the same as A. So check those answers. A at time t+1 is equal to B and C. B at time t+1 is equal to not B and C, or B and not C. C at time t+1 is equal to not A and not C, and Z is equal to A. Okay, so that's correct. Okay, now let's do the state table for this example. We have to note that these A-B-C- does not mean negative of, it means at time t+1. So you can read it as A- being A at time t+1. So now we have the equations from the previous slide. A at time t+1 is equal to when B and C are both 1. B is 1 here, C is 1 here. So we have A- being 1 here and here, and then 0 everywhere else. For B at time t+1, B dash, we have it equaling to 1 when B is 0 and C is 1. That is, B is 0 and C is 1. This means here and here. Or when B is 1 and C is 0. B is 1 and C is 0. It's here and here. And then 0 everywhere else. For C at time t+1, we have it being 1 when A is 0 and C is 0. A is 0 here, C is 0 here and here. We have that being 1 here and 0 everywhere else. And for Z, the output, quite simply, we have it whenever A is equal to 1. So that is all of these values down here, 1, 1, 1, 1, and 0 everywhere else. So check that answer. That looks okay. Okay, now based upon this state table from the previous page, let's draw this state diagram up. So it starts with a reset back to state 0, 0, and from state 0, 0, we move to state 0, 0, 1. So from state 0, 0, 0, we move to state 0, 0, 1. From state 0, 0, 1, we move to state 0, 1, 0. From state 0, 1, 0 here, we move to state 0, 1, 1. And then from state 0, 1, 1, we move to state 1, 0, 0. And from state 1, 0, 0, we move to state 0, 0, 0. Don't worry about my drawing, I'll draw it up neater after this. So you can see that it really just counting from 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 0. So 0, 1, 2, 3, 4, and then back to 0 again. And in terms of the outputs, we have it giving an output of 0 for the counts between 0 and 3. And then when we count between 4 and go back to 0, then we have an output of 1. So this is where we get the 1. And then there are these other states here at the bottom, which you have to say are basically invalid states. Let's write over here 1, 0, 1. And the reason why I write it over here is because I can see it's going to change to 0, 1, 0, which is here. So if we happen to start at an invalid state like 0, 1, 0, then after one clock pulse, we simply move to 1, 0, 1, and then we'll continue in this loop. Another one is if we start at 1, 1, 0, then we also move to 0, 1, 0. So that's 1, 1, 0, another state that goes into 0, 1, 0, and then into this loop. And finally, 1, 1, 1 goes to 1, 0, 0. So let's write it near this one. 1, 1, 1 goes to this. So that means after a reset, you start at 0 and you count from 0 to 4, and then you give an output of 1 every time you count to 4 and go back to 0. If you happen to start on these invalid states, then after one clock pulse, you'll be back on a valid state, and then you'll continue around this loop. Notice that there's no X in any of this, so it doesn't matter what the input state is. After it's reset, it starts at 0, or if it's on any of these invalid states, it moves to a valid state and then continues looping around and counting up. Here's a cleaner one that I just prepared, better than my drawing, and I hope that's cleared up the process after those two sequential circuit analysis examples. And that's the end of the first part of the sequential logic lecture series, and I hopefully catch you in the next lecture where we'll cover more complex sequential logic. So see you then.